In this series, we are going to work on 2004 gate paper for the electrical branch. Now the first question reads, the value of Z in figure 1, which is the most appropriate to cause parallel resonance at 500 Hz is. So we have our options. A says 125 millihenry, B 304.20 microfarad, C 2 microfarads, and D 0.05 microfarad. So in this problem, we are supposed to figure out the element Z, whether it is an inductor or if it is a capacitor. So the first thing we will have to note is that the question says parallel resonance. Now in this case and in this figure, you will notice that the element Z is in parallel with the inductor. And since it says parallel resonance, you should know what resonance is. Now at resonance, what happens is that the admittance of a circuit is at its minimum, or in other words, the impedance of a circuit is at its maximum. So let's take the admittance of this circuit and write down the equation for the circuit admittance. So here, the admittance of the given circuit is what we're going to write down. Let's call this Y. So Y would be equal to YL plus YZ. Now note that we are going to find out the parallel resonance, right? So we will have to consider these two elements alone, the inductor and Z. So Y would be equal to YL plus YZ. Now at resonance, I mentioned that the admittance is supposed to be minimum. So in that case, what happens here is YL plus YZ should be equal to 0. That's the only way the admittance of a circuit would be minimum. Now let's write down the expression for inductor admittance. Now here YL will be written as 1 by J omega L, and YZ can be written as 1 by Z, which is equal to 0. Now for this equation here, if we solve for Z, we will get a certain expression. So let me write that down here. Okay. So the expression so far, 1 by J omega L plus 1 by Z is equal to 0. Now if we solve for Z, we will obtain an expression of Z equals to omega L by J. Now this part over here tells us that Z element is capacitive. So because it is capacitive, we use the capacitive expression of C is equal to 1 divided by omega square L. Now this is the formula, please make note. C is equal to 1 by omega square L. So we have the values already given to us. We have omega given as 500 Hz, or this is frequency F. We have the frequency as 500 Hz, and we have the value of inductance given to us as 2 Henry. So let's substitute the values into the capacitor expression here. So C is equal to 1 divided by 3.14 times frequency 500. This is omega, 2 pi f, right? Into 2. So all of this, right. Okay, so that's 1 divided by the entire thing here. Now if you solve this expression, you will get a value of 0.05 into 10 power minus 6. And that's 0.05 microfarad. Now checking with the options given to us, 0.05 microfarad matches with option D. So this is the solution, and I hope it has helped. Here's the next question in the series, number 2. A parallel plate capacitor is shown in the figure. It is made of 2 square metal plates of 400 mm size. The 14 mm space between the plates is filled with two layers of dielectrics of epsilon r equals 4 at 6 mm thick and epsilon r equals 2 at 8 mm thick. Neglecting fringing of fields at the edges, the capacitance is. We have our four options given to us. The options say that A is 1298 picofarads, B is 944 picofarads, C 354 picofarads, and D 257 picofarads. Alright. So here in the figure you will notice that we have two plates and epsilon r and the distance has been given, the thickness has been given. And here epsilon naught value is 8.85 into 10 power minus 12. So let's first write down what's given to us. All the information, let's put it down. So here we have given data. First, the side of the metal plate is given as 400 mm. So that's side 400 into 10 power minus 3 meters. Then let's write down the area. Area is side square. So that's 400 into 10 power minus 3 square. Let's call this epsilon r1 and let's call this epsilon r2. And likewise, the thickness is d1 and d2. So we write that down. Epsilon r1 is 4. Thickness d1 is 6 into 10 power minus 3. Epsilon r2 is 2. Thickness d2 is 8 into 10 power minus 3. So this is the given data. Now the next step is to find out what the equivalent capacitance is. Now in order to do that, we will have to calculate the capacitance of each of the two plates given to us. Okay, so let's start by writing down the expression for equivalent capacitance. If we consider the capacitance of plate 1 as C1 and the capacitance of plate 2 as C2. Now both of them are parallel plate capacitors. Okay. Now we write down the equivalent capacitance. So the equivalent capacitance, C equivalent, I'll write that down, is written as C1 C2 divided by C1 plus C2. Now this is because the question says that they are parallel plate capacitors. So C1 and C2 are arranged parallelly. And the expression would be C1 C2 divided by C1 plus C2. Now let's write down the expression for capacitance for each of these parts. Now we know for a fact that C, the capacitance of any element, is written as epsilon naught times epsilon r area divided by thickness. Now if we substitute this into the equivalent circuit or the equivalent expression, let's write that down, that C equivalent is equal to epsilon naught epsilon r1 A divided by d1 times epsilon naught epsilon r2 into A divided by d2 all over epsilon naught epsilon r1A by d1 plus epsilon naught epsilon r1A by d2. Now let's simplify this further so that the substitution of our values will become a little easier. Okay. Now what can we take common over here? I believe we can take epsilon naught into A common in the denominator. Let me just note that down here for you. So this would be epsilon naught square, since we have epsilon naught there in the numerator. So that's epsilon naught square times area square epsilon r1 into epsilon r2 whole divided by, let's see, d1 d2. Now further, we can take epsilon naught into A as the common part. we'll be left with epsilon R1 by D1 plus epsilon R2 by D2. So here we can cancel out epsilon naught and epsilon naught in the numerator. Now the rest of the portion, I believe we can cancel out the area as well, one part of the area. So this is what we have. Okay, I'll note this down over here. So C equivalent is equal to epsilon naught A, epsilon R1, epsilon R2 divided by epsilon R1 D2 plus epsilon R2 D1. So this is a simplification of this to the next step. Now all we have to do is just plug in the values of these terms. Okay, let me just grab another sheet of paper. We'll substitute the values here. Here, what do we have? Let me write that down. C equivalent is equal to 8.85 into 10 power minus 12 times 400 into 10 power minus 3 whole square into 4 into 2 divided by, okay, here we have 4 times 8 times 10 power minus 3 plus 2 into 6 into 10 power minus 3. Now solving this, you will obtain a value of 257 into 10 power minus 12. Well, that tells us that the final answer is 257 picofarads, since 10 power minus 12 is pico. Well, this is our final answer. Let's see what value it matches with. Matches with option D. So this is the final answer, and I hope the solution has helped. Here's the next question, number 4. The total instantaneous power supplied by a three-phase AC supply to a balanced RL load is, now we have our 4 options: 0, constant, pulsating with 0 average, and pulsating with non-zero average. Now, in order to see what type of power supply is given by the balanced RL load, we will have to take into consideration our phasor diagram. Now we know that for an AC supply to a balanced RL load, if we consider this A, B and C, okay? So you know that each phase the angle is 120 degrees. They are 120 degrees apart. Now since we will have to take the total instantaneous power supplied, now let's work it out and then see what the result tells us. The result will tell us what type of supply it could be. So let's start. Now the power for an AC supply, three-phase AC supply, can be written as VAIA plus VBIB plus VCIC. Now let's expand each one. VA in terms of the maximum voltage can be written as Vm sine omega t. Okay? But the current will then be written as Im sine of omega t minus phi. This is for VAIA. Next, let's write down for VBIB. Here we will have Vm sine of, okay, now since we started with VA, VB would be omega t minus 120 degrees. And then IB can be written as Im sine of, okay, so what will we get over here? Omega t minus 120 minus phi. Okay, so this is VBIB. Similarly, let's write down for VCIC. Now for VC, we will have Vm sine of omega t minus, this time it would be plus 120 degrees. And Im will be written as IC. In fact, IC will be written as Im of sine omega t plus 120 minus 5. I hope this is clear so far. Okay, so now let us write down and solve each term. So if we solve each term, Vm, and here we have sine omega t and sine of omega t minus 5. So recall your trigonometric formulas. Sine A, sine B can be written as, let me just write that down over here. Okay. So our instantaneous power, we are going to start with the first term. Now for the entire part, now you see here Vm, Im, let's just write that down as Vi. So we are going to take Vi common throughout. Okay? So now sine A, sine B can be written as what in terms of cos? We have a formula. Okay. Now the trigonometric ratio sine A, sine B is written as 1 by 2 cos of A minus B minus 1 by 2 cos of A plus B. So we are going to use that in order to expand this further. So previously here we have sine of omega t into sine of omega t minus 5. So that will now become cos phi minus cos of 2 omega t minus 5. Similarly, for the next term, what do we have for the next part? We have sine of omega t minus 120 and sine of omega t minus 120 minus 5. So that will become cos of phi minus of cos 2 omega t minus 240 minus 5. And finally, for the third term, the third part, sine omega t plus 120, sine of omega t plus 120 minus 5 would be written as cos phi minus cos of 2 omega t plus 240 minus 5. Work it out using the trigonometric identity as I said a little earlier, and you should be able to get this. Now here, if you see closer, now cos phi is what is most important here. So the power can be reduced to 3 Vi cos phi. Now 3 Vi cos phi indicates that the total instantaneous power is constant. It is not zero and it doesn't pulsate as well. So the final option over here is B. The total instantaneous power supplied by a three-phase AC supply to a balanced RL load would be constant. Here's question number 5. A 500 kVA three-phase transformer has iron losses of 300 watts and full load copper losses of 600 watts. The percentage load at which the transformer is expected to have maximum efficiency is. So we have our options. The options are A 50%, B 70.7%, C is 141.4%, and D is 200%. Okay. So the question here asks for the condition of maximum efficiency. Now in order for the transformer to have maximum efficiency, now let me write that down here. At maximum efficiency, the copper losses must be equal to the iron loss. Okay? So if we have to write an expression in this case, K square copper loss equals iron loss. Now the ratio here is in terms of K square. So the K is the load factor. Okay? This is load factor. So now what would we have? We would have here the percentage load. Now the percentage load is the load factor. So K would be equal to root of Pi by Tcu, which means it is the ratio is the root of the iron loss divided by copper loss. Now we have our expression, the values given. Iron loss is 300 watts, copper loss is 600 watts. So that would be root of 300 divided by 600, which when solved gives us 0.707. Now 0.707 in terms of percentage would be 70.7%. So here the right answer is B. Here's the next question, number 6. For a given stepper motor, the following torque has the highest numerical value. We have A, dead-end torque, B, pull-in torque, C, pull-out torque, and D, holding torque. Okay. So, in order to actually find out what type of torque would be the highest in terms of numerical value, we will have to take the torque versus pulses relationship. So, let's draw the waveform or the diagram over here, the characteristic diagram, okay? So, here we have the pulses per second. So, that's PPS. And here we have our torque. This is torque versus pulses. And we will have to find out the maximum torque. Now the maximum torque is supposed to be the steady torque. Now which one of these would give us the maximum numerical value? That is what we will have to find. Now in terms of pulses, our characteristic expression is something like this. Now here at this point is the maximum pull-in, and at this point is the maximum pull-out. So at pull-out you will notice that the torque is at the highest numerical value, this part over here. Now the shaded region indicates the slew range. Okay, so this portion over here is what gives us the numerically highest value, and this denotes the pull-out torque. So the right answer over here is for a stepper motor, the torque, which is the pull-out torque, has the highest numerical value. So answer C is the right option. Here's the next question, number 7. The following motor definitely has a permanent magnet rotor. So we have A, DC commutator rotor, B, brushless DC motor, C, stepper motor, and D, reluctant. Now out of all of these different types, the stepper motor, which is also a brushless DC motor, is the one that uses a permanent magnet type of rotor. Now this is because its rotor moves in discrete steps. Now that is why a stepper motor is the one that definitely has a permanent magnet rotor. Okay, here's the next question, number 9. So here the question says that the direction of rotation of a 3-phase induction motor is clockwise when it is supplied with 3-phase sinusoidal voltage having a phase sequence of A, B, C. For counterclockwise rotation of the motor, the phase sequence of the power supply should be what? So our options are BCA, CAB, ACB, BCA or CAB. Okay. So in order to know the counterclockwise rotation, what happens is, to reverse the direction, any two phases can be interchanged. So here, for clockwise direction, we have the sequence of A, B, C. So in order to reverse the direction, any two phases can be interchanged. So AB can be interchanged, BC can be interchanged. So in this case over here, it can be either ACB or it can be let's see now, B, A, C. So it can be any one of these two. So you see here, what we have done is either interchange these two or interchange these two. Okay, so any two can be interchanged. So it can either be ACB or BAC. Now in the options given to us, only one matches. ACB matches. So ACB is the right answer here. Here's the next question, number 10. For a linear electromagnetic circuit, the following statement is true. Field energy is equal to the core energy. Field energy is greater than core energy. Field energy is lesser than core energy, and core energy is 0. Okay, so now before we get into which statement is actually true for a linear electromagnetic circuit, let's just briefly go into what is field energy and what is core energy. Now, we know that for any circuit or for any type of field, now the field energy is a description of both types of electrical field and magnetic field. Now, both of these types of fields, they store energy, isn't it? Both electrical fields and magnetic fields store energy. So this energy is known as field energy. And on the other side, the core energy is actually also known as dual energy. It is a non-physical quantity, really. So this non-physical quantity can be measured in terms of, is same as the energy unit, and it is usually used in theoretical analysis of storing systems and transferring of energy. So if we have to go back to the basis of Newton's laws, you should be quite familiar with what conservation of energy is. That energy can neither be created nor can it be destroyed. It can only be transferred from one type to another. So you're quite familiar with that because that's what we have all learned in the beginning of working on in physics. So for a linear electromagnetic circuit, the field energy, the type of field that is used in the circuit can either be an electric field or a magnetic field, and its corresponding core energy of the of a certain situation or a certain circuit per se, it has to be equal. Conservation of energy depends on the fact that both field energy and the core energy is absolutely equal. There has to be a balance in the entire circuit, balance in the system and balance in the equations. That's the essence of the entire thing. So here, the field energy has to be equal to the core energy because of conservation of energy. Okay, here's the next question, number 11. It says that the rated voltage of a three-phase power system is given as RMS phase voltage, peak phase voltage, RMS line-to-line voltage, and peak line-to-line voltage. So this is another theory question. Now basically the rated voltage of a three-phase system is always given by RMS value of line-to-line voltage. That's actually the basic here. So you just have to remember this. So the rated voltage of a three-phase power system is always given by the RMS value of line-to-line voltage. Okay, here's the next question, number 13. In thermal power plants, the pressure in the working fluid cycle is developed by, so the four options are condenser, superheater, feed water pump, and turbine. So the working fluid cycle, or in this case it is actually called the Rankine cycle, it is the process that describes the steam operation in the heat engines that generate electrical power. So this is actually a closed loop cycle. So there are four specific components. All the four over here are given as the options. So we have the first one, which is a boiler, which is then connected to the turbine. then further to the condenser, and then to the pump, which is further connected back to the boiler. So this cycle is the working fluid cycle. So here, among our four options, the first is a boiler, so we can consider that as the superheater. Now the superheater, what it does is it heats the steam that is generated by the boiler already. So it is actually connected between the boiler and the turbine. Now you know that in thermal power plants, the diagram or the components in a thermal power plant, they are more than the four basic components given over here. So the superheater is somewhere between the boiler and the turbine, and the function is that it reheats the steam that is generated by the boiler. So this actually increases the thermal energy. So if you notice that there is no such thing as the pressure in terms of a superheater. So now the turbine, what it does, using the steam from the superheater and the boiler, the blades of the turbine start turning, and because of that, the mechanical energy is then converted into electrical energy. Now what happens to the steam that hits the turbine? It comes to the condenser. So here we have our condenser in the option here. So what the condenser actually does, it condenses the steam, or it converts the steam from the turbine into water again. So that water needs to be pumped back into the boiler. So that is the function of the feed water pump. Now the function of pumping the water back into the boiler comes the factor of the pressure. Now the pressure in this entire cycle is developed by the pump, or in this case by the feed water pump. So the right option for this question is feed water pump, option C. Okay, here's the next question, number 14. For harnessing low variable water heads, the suitable hydraulic turbine with high percentage of reaction and runner adjustable vanes is A. Kaplan, B. Francis, C. Fulton, and D. Impeller. Now among all the four options, you should be able to guess immediately that Francis, Fulton, and Impeller are all used for high water head functions, but Kaplan is for low water head. So that in itself gives us the final answer, because for low variable water heads, Kaplan is the best choice. Francis, Fulton, and Impeller are all the three for high water heads. At different flow rates of water. So, well, the final answer is Kaplan in this case. Here is the next question, number 16. The current through the Zener diode in figure given is, we have our four options, 33 milliamps, 3.3 milliamps, 2 milliamps, and 0. So, in the figure over here, you will notice that on one end we have our source of 10 volts, and the voltage across the resistor R1 is 3.5 volts. We will have to find out the current through the Zener diode here, given as IZ. So, using the basic Ohm's law, we can say that the current is equal to V by R. We know that. So, in terms of Zener diode, IZ would be equal to the difference in the voltages, delta V divided by RZ. So, delta V is the difference of the two voltages over here, which is 3.5 volts minus the voltage VZ divided by RZ. Now let's further substitute the values over here. We have 3.5 minus VZ is given to us as 3.3 divided by RZ. RZ is 0.1 K. Now if we solve this, you will get a value of 2 into 10 power minus 3, or 2 milliamps. So here for this problem, 2 milliamps is the current through the Zener diode, and that matches option C. Here's the next question, number 17. Two perfectly matched silicon transistors are connected as shown in the figure. The value of the current I is, so we have our four options, 0, 2.3 milliamps, 4.3 milliamps and 7.3 milliamps. Okay, so here in this case, we see that there are two silicon transistors that are connected, and on the left side we have a resistor of 1 kilo ohms. Now, the current that is passing through the 1 kilo ohm resistor is IR, and the current that is passing through the transistor here through the collector is IC1. On this side, the same current that is passing through the collector side of the transistor is IC2. So, practically we will have to find out what IC2 is, because that is I given to us. And the beta values for both is 1000. And here we have a voltage of plus 3. On this end we have minus 5. And over here we have 0.7 at node B. Now I am calling that node as node B. Okay. So the first step is to calculate the current that is passing through the resistor over here. Okay. So I'll write down the formula, the direct formula. So the current through the resistor is equal to the difference in the voltage divided by the resistance R. Now the difference in the voltages in this case is the voltage over here at base and the voltage over here minus 5. So at base here you will see that there is a positive value here and a negative value over here. So minus of minus 5 minus 0.7 is the difference. So that's 5 minus 0.7 divided by resistance is 1K. So if you solve this part, we will get the current that is passing through the resistance, which is, it comes to 4.3 into 10 power minus 3 amps. This is the current of the resistance. Now, because we will have to calculate the current of the collector side of this transistor over here, let's use the following formula. Let me just grab another sheet of paper. Okay. So, to find the equation, we can write down the formula as IC1. That is what we need over here. Okay. That is written as beta divided by beta plus 2 into IR. For this specific circuit, to find out what is IC2, IC1 is anyway equal to IC2, so they are the same, okay? IC1 will be equal to IC2. So the formula is beta by beta plus 2 into IR. So what do we have over here? IC2 is equal to 1000 divided by 1000 plus 2 into IR, which is 4.3 into 10 power minus 3. Now you will notice over here that beta is very high, right? So we see that beta value is very high. So in that case, the part which is this can be easily ignored, and we will be left with the value of 4.3 into 10 power minus 3. So IC2 value is the same as IC1 value, which is also the same as the current that is passing through the resistance, which is 4.3 milliamps. So this is the final answer. Now the key over here is to note the value of beta. Now because the value of beta is really high, so the current of the collectors of both transistors will be equal to the current that is passing through the resistance. So in this case it is 4.3 milliamps, and that matches option C. Well, this is the entire solution, and I hope it has helped. Okay, here's the next question, number 19. The digital circuit using two inverters shown will act as A, a bistable multivibrator, B, an astable multivibrator, C, a monostable multivibrator, and D, an oscillator. So you'll notice here in the circuit given that two inverters are connected. Now these two inverters are connected in sort of a series fashion. Now because they are connected this way, they behave as a bistable multivibrator. Now here A is the right option. So in this case what happens is, now both states of 1, 0 will be stable, and alternatively with both of the inputs will be 1 and 0. So that is why when two inverters are connected this way, they behave as a bistable multivibrator. Okay, here's the next question, number 20. The voltage comparator shown can be used in the analog to digital conversion as A, a 1-bit quantizer, B, a 2-bit quantizer, C, a 4-bit quantizer, and D, an 8-bit quantizer. So in the figure given over here, you will notice that V1 is connected to the positive terminal, V2 is negative, and of course the output is V0. So here V1 and V2 are the inputs. So you will have to take into consideration when one input is greater than the other in two different ways. So here let's consider when V1 is greater than V2. When V1 is greater than V2, here we will notice that V1 is positive, right? So the value of V0 or the output V0 is high. Okay. Now in the next case, V1 is less than V2. So when V1 is less than V2, the output V0 is low. And why is that? Because V2 over here is negative. Okay. Now because it has an alternatively high and low output ratio, the voltage comparator is a 2-bit quantizer.